In this video, we'll be looking at the efficiency of a small electric motor. If you turn to page 130 of the textbook, you'll see this experiment. Now, I don't have a nice little pulley system or preset masses, so I had to improvise. I'm going to briefly go through how I improvised the experiment. This is what it looks like in the book. I already had a little DC motor. It's just a 1.5 volt motor, and I stuck some blue tack to the bottom of it and hence stuck it onto the edge of the table. I wrapped some cotton like this around the spool, and instead of using preset masses like it has in the book, I just decided to use stones of different sizes, like these. I found the mass of the stones and used different combinations to make different masses. So they just got placed in this little bag here, which is suspended from here. Using a meter rule, I measured the total distance it travelled, and that was 0.64 meters. Step 1. Find the potential difference across the motor. I'm using a 1.5 volt battery, so I've put the voltmeter in the 2 volt range. I'm putting the voltmeter in parallel with the motor, and that gives me a reading of 1.558 volts. Step 2 is lifting the load. We'll start off with 12 grams, although you can start off with any value that's appropriate. Are we ready for the ammeter reading? 3, 2, 1. That's 0.41 amps. Now we're going to repeat the experiment because of the large possibility of experimental error. 3, 2, 1. 0.39 amps. So for a mass of 12 grams and a potential difference of 1.56 volts, we get an average current of 0.4 amps and an average time of 0.95 seconds. So you may ask yourself, how did I work it out to be 0.95 seconds? Well, I used my video editing software. I record the time when the motor starts, and then the time when the masses have reached the top. The difference in these times gives the time taken. We then tabulate the results. This is what my results look like. You can work out the power input by multiplying the current and the voltage. You can calculate the work done against gravity, mgh. Work done divided by time taken gives the power out, and power out divided by power in gives you the efficiency. You can see the efficiency starts to fall after a load of about 0.273 newtons. What happens with even heavier stones? Well, the experiment got a bit more frustrating. 3, 2, 1... Great. But with a bit of patience, we can get a few more results. I kept going up to 42.1 grams. 3, 2, 1. Done. Here's a summary of the results for the largest stones. If we plot efficiency against weight, we get an optimization curve like this. Here the optimum is about 20% for a load of about 0.27 newtons. But that will be different for different types of motor. So don't worry if you're doing the experiment and your values are different. Now it would be very tempting to forget about those nasty random errors that you can see on the far right of the graph. But it is important in physics to not just ignore the results that you don't like. We can learn a lot from those results. For one, we can think why these results had such large random errors. Some possible contributions to the experimental error are to do with the timing. Well, even though the time was measured to the nearest 100th of a second using the video editing software, it still relied upon my reactions to determine the start and end point. Probably the biggest contribution to the experimental error is my reel was not very sophisticated, so the thread could easily get caught and the friction may not have been very consistent. There was also a problem with the heavier masses swinging when they were being pulled up, which would affect the efficiency. And another problem was the lagging of the ammeter. How would you execute the experiment to reduce experimental error?